So let us start. Seminar today is Zoran Škoda from University Zadar and the University of Hradec, Králové. So he's a frequent participant of our seminar, so I don't need to how to say speak more on his research interests, and today he shall speak on the very exciting problem on Nonabelian Čech cocycles in noncommutative geometry. Please, Zoran.
Okay, thank you very much for opportunity to speak again in this seminar. So actually in this seminar, I gave two talks. One was live and it was on Hopf algebroids, and another was a related talk on bundles, on quantum flag varieties and non-commutative flag varieties in general. And that talk is somewhere online. There is a presentation on the YouTube. So this talk is related, but it's different aspect, and it's not about examples. It is in fact about general theory, and so let me be gentle, because most of people here do not work actively in non-commutative geometry. So let me remind you of usual Czech cohomology first, and then to motivate so-called Svidler coring, and then I will talk about non-commutative geometry, and then about the main subject, these cocycles. I should also mention that there is a very old preprint of mine which is wrong on the archive from 2011, which has major mistakes, and it can be corrected, and once it will be replaced, there are just some beginning ideas over there. So say that you have some space Y, some space, usual space. I'm just repeating the usual setup, and that we have some cover, some U alphas, some family of maps U alphas to Y. Then you can consider a product of all U alphas and take that as just one map to Y. And then we can consider this multiple products, U alpha beta, product U alpha to Y, and so on, and make a simplicial object in spaces, simplicial object in spaces. And then if you apply functions on each of these, some sort of functions, depends on which category of spaces you are, then you see if I'm taking, say, U alpha cross U beta over, then this should be some sort of tensor product. And if there is some, if this is over something, then here should be also some tensor product which is relative over something. Then if you apply the algebra, if you apply taking some sort of functions on the space, that's usually functorial, depending which kind of functions or cocycles you are taking. And then this is contravariant, and you will have maps in opposite direction. And then you will, on the level of these algebras, so if I call this some product of A alpha, this is some different product, maybe tensor product or something, then you will have a maps in opposite direction, and I will have cosimplicial algebra. I will have cosimplicial algebra. So now there is, if you consider this situation, that if I will call this product, if I call this as single space X, then if I have this cover X to Y, now I will have OY to OX, and these are some algebras. Say that this is some R, this is S, Then I will have objects like this. S tensor S over R, and I'll have some sort of co-simplicial object like that, and you can associate a complex by usual rule, and this is usually called Amitsur complex. On the other hand, you can consider also modules over R, and you can consider modules over S. And then if you have a map from R to S, if you have, say, a ring morphism of rings, then I will have, for morphisms of rings, I will have a number of functors between, I will have actually 3 functors between S modules and R modules. I will have a restriction of scalars, I will have extension of scalars, and extension of scalars is left adjoint. So module goes to S over R M if are left modules. From R modules to S modules, that's extension of scalars. Then restriction is just replacing the coefficients, the scalars, and the restriction has its own right adjoint. So it's important thing that we have a joint triple, not only a joint pair, but a joint triple. Now, in this setup, there is a classical question of descent theory, usual question of descent theory. So descent theory in this example wants to solve the following problem. You want to consider modules over S, and you are interested when modules over S come from modules over R by this extension of scalars. And can you reconstruct this category modules over S from modules over S? That would be this in this particular example from the beginning. If I would have some, say, bundle or sheaf over each of these U alpha, so over the product of these U alphas, and then you want that they agree on the intersections, and if they agree on the sections, they will define a global object on Y. So this product is basically this product of algebra tensor product is actually here. Here you have basically some sort of co-product. Tensor product is a co-product in the category of commutative rings. For non-commutative rings, it's a free product. There is some problem with this, but it's actually not a problem if you understand what you are doing. So then this is usually this descent problem is usually stated in terms of this co-simplicial object, that above every level of this, so if I have this S tensor S, S tensor S tensor S, above every level, you consider a module N here, then say N0, I will have N1, I will have N2, and then you can have extension of scalars along each of these maps. So you will have that that you will have extension of scalars of this on the next level, and then you are interested when they will match, that there are some morphisms, some isomorphisms that they will match at all levels, and it is enough that you match them at the level of isomorphism at the level 1. So and this isomorphism is a part of data, and then you create so-called descent data. They make a category, and this category is in good cases of under some assumptions on this homomorphism from R to S. This is basically saying that you have some sort of covering condition in classical case. Here is more complicated in non-commutative case. And then you will be able to reconstruct the modules over R. So this is basically taking, if you take the pseudo co-simplicial object induced from these functors. So you have these maps of rings. They will induce functors at the level of categories of modules at every level. And you will have this pseudo co-simplicial object, and you take basically its limit, and this limit will be category of modules over R. That's a standard story, which I will not explain the details. It is just motivation. It is motivation. I will explain how it looks like in our case. It will be a little different in our case. So let me go further. New page. Before I go to this, let me say what non-commutative geometry is about. So non-commutative geometry. So non-commutative geometry is a general subject in which space is defined by all objects of certain kind, objects over that virtual space. So simply define space by all objects which live over the space. So so first, why is this a good philosophy? Because in commutative geometry, you have so-called reconstruction theorems. What do reconstruction theorems say? That you have some classical notion of space, say a topological space or differentiable manifold, or say that somebody or something in topos theory, but it's more classical than non-commutative in a sense. Then you take, you take spaces, you have object like, then over space, what can live? You can have functions over space. You can have sheaves over space. You can have, say, coherent sheaves over space. You can have maybe derived category of sheaves over space. So this here make an algebra. Maybe it's operator algebra. And this here make category. And this is maybe higher category. Maybe higher or derived category, higher category. And then there are theorems that if you take some good category of such algebras, you get category of spaces by some sort of duality. So you have, say, Gelfand-Naimark theorem here. Then you have Giraud's theorem in sheaf theory, in topos theory. Then you have reconstruction theorems in non-commutative geometry, like Gabriel-Rosenberg theorem, which reconstructs scheme from the category of quasi-coherent sheaves. Then sometimes you can do from derived category of sheaves. You have Bondal-Orlov theorem, for example, and so on. So space is defined by such things. Now, important point is that if this, these sheaves form an ordinary category, but coherent sheaves make an abelian category. And here are, say, triangulated categories. And nowadays it's very popular that people do derived geometry, that they do derived categories instead of abelian categories. And over there, many things are much more commutative. Homological algebra is basically coming from topology. Things basically work quite commutatively. And if you work at the level of coherent or quasi-coherent sheaves, then you are working with, say, abelian category. And with abelian categories, many things are much more difficult. And many of the things which I apply today, which I say today, many of the problems which I will allude to are actually problems here, and here things in a way simplify. So this is a little bit harder setup for than higher category setup for many questions which I will be which I'm concerned. So that's one thing. And second thing is that these two, that some people consider algebras and some consider abelian categories. So this is non-commutative algebraic geometry. Say not operator algebras, that just algebras, rings, non-commutative algebra. Of course, commutative, if it's non-commutative means I'm taking not coherent sheaves, but I'm taking some abelian category. And here I'm not taking algebra of functions, which is commutative, but I'm taking some algebra. Then it becomes non-commutative algebraic geometry. So important thing which I wanted to say is that in some problems, it is important to mix algebras and categories. What this means, you see, if you have a ring, R, and you consider the category modules over a ring R, Rm. This is the way we say in Hopf algebra theory. That's R modules. There are reasons we usually have some base category M, and then we have various new actions on this basic category. So say that you have a ground ring, say Z, and then modules over Z is this M, and then you add another things which are maybe some co-algebras or some Hopf algebras at various places here, which act or co-act at some places. And so this ring R, first question is, can I reconstruct the ring R from modules over ring? Yes, to some extent. You know that in non-commutative situation, there are Morita equivalent rings which have the same category of modules. And many people kind of say that non-commutative geometry should identify this because most of the invariants will not care whether I talk about R or I talk about some other, say R prime, that is the same category of modules. This is not the point of view I will take. Of course, this is true, and for many things you have to work on up to Morita equivalence, but identifying is kind of wrong because you don't care about automorphisms and you don't have local coordinates, preferred choice of local coordinates. And these two things are important for many problems, automorphisms and local coordinates. So I really want to have not only category, but I want in this category to distinguish one object. You see, if you have a projective generator here, that is projective, finitely generated projective module, then take endomorphisms of this module M opposite, if I'm working with with left modules, and this will have a natural structure of a ring, and this is exactly the ring R. This is a reconstruction. So if I have here a choice of, so I have some category, say C is a category, and I have a distinguished object, oh, this is like a structure sheaf. Then I have abelian category, and I have distinguished object there. When I have situation like that, then you have a control of say local coordinates. You have a control of choice. This is a choice in Morita equivalence class. Morita equivalence class. Choice in Morita equivalence class. So this is not the main reason why this O is useful. This is just a kind of a general matter. There is a different one. You usually have so in non-commutative geometry, some examples start with algebra, with some algebra of non-commutative algebra of functions. So you can consider, say, you have some generators, say x1 to xn. I will put with heads. That means they do not commute. And these are generators, say, of finitely generated algebra. There are some relations, non-commutative relations. And you consider this as some sort of coordinates, kind of basic coordinates in some. So this is some sort of A is generated by this modulo some relations. Maybe it's better to say A is an algebra. Then this algebra is say showing local coordinates, but if you want to have something like analog of projective space, then you know in usual algebraic geometry you cannot work with just a single algebra. You need to have something like a scheme. You need to glue several algebras. You need A1, A2, A3, and so on, and you have to glue them. But you cannot glue them in the category of algebras. You cannot get a global algebra. Instead, I have to consider for each of those. I have to consider modules over A1, modules over A2, modules over A3, and so on. And you want to glue all of these categories. You want to glue all of this to get some global category M, and to have some global kind of structure sheaf O, such that O, when I would restrict to this category, and restriction will be some sort of a pullback functor. Like here I had this R to S, I had category of modules, and you have extension of scalar. So you have F, and you have F upper star was extension of scalars. So similarly, you have here some functor from M to MA3, say call it M3. And this would be some sort of inverse image functor. In general, it will have to have a right adjoint. It has a right adjoint F lower star if this is F upper star. You will have such a situation. And so these examples come very naturally. I will today not talk that much about examples. So but I will talk about situation where I will have two such. So like before, I had this cover U alphas over some Y. Now I will have some big category A for abelian category, and I will have, instead of going inside, I will have going outside, because I will look at these inverse image functors. B say alpha, and there is the whole cover of such. And right adjoint, if you would consider the right adjoint, then it would be like this. Right adjoint is in the geometric sense. This is in anti-geometric sense. In the opposite sense, this inverse image functors, they look like maps of rings. And you want to have to glue this A from B alpha. This is a relatively standard thing, but I will have one more thing. I will have actions. I want to consider Čech for principal bundles. And then from these principal bundles, I can do associated bundles. At some level, theory works nice for associated bundles as well, but there are also things where for associated bundles, there are problems which do not exist for principal bundles. And so I will remind you of the situation with principal bundles. So if this is my space and this is its cover, I would like over every of these have a locally trivial, I will have over A to have a locally trivial bundle, which will trivialize over this B alpha. So I have to know what does it mean trivial. And that depends on the generality in which I want to look at. So I will have this cover, I can glue this A from B alpha by descent theory. But I want also to have above it some space. So I say A tilde and here B alpha tilde, which are like total space of a principal bundle and total spaces of these parts. So I will tell you how to do that in a class of cases, and this will lead to very, very concrete, not at the level of functors, but really algebra maps, bimodule maps, some actions, and so on. It will be very, very concrete data, and that's basic. So this here is not. I mean, this is known 20, 25, 30 years ago. I'll talk about new things here, but I need to give introduction. There are many details here, how to do the gluing, etc. Some of these things will appear in a little bit. Let me consider the usual principal bundle in commutative geometry. So what do you have? You have a group G acting from the right on some space E, which is over some Y, and this is free action, and it's continuous, and moreover there is a map tau, which goes from E cross E over Y, all those pairs which are in the same fiber, into G, which basically translation map, which basically tells which G element is needed. If you have E prime, then it gives that G such that E prime is G times is E times G, and it's required that this is continuous. Now, if you have a section of this, so what is a section? Section tells you that it's trivial. Section S from Y to E. Then you can take any E in E, and to this E you assign what? I take E, and then I can project it if this is E is the projection. I can project it and then take the section of E. And these are two guys in the same fiber. Take two of that. I get element in the group and take some function in the group. And some fixed function. So if I have a map which F sends to this will be a map from functions on G to functions on E. You see this function on E because E is in E. So that means that these algebra of functions on a group, because all maps bank functions go in opposite direction. So this is not just an algebra, but because underlying you have a group, you will have a map in opposite direction. So we have a co-multiplication from O of G to O of G cross G or O of G.
Zoran?
Yes.
Zoran, sorry. This is Rita. I
Yes.
have a question. So is an affine object, is that right?
Yeah, I'm here affine for the moment.
Affine, sorry. Okay, thank you.
Actually, in this situation, I'm working continuously, even continuously. But now, now I'm starting to get affine at this point, exactly at this point.
Okay, thank you. Thank you very much.
But of course, I will not be only affine. You will see I will not be affine, but all the time. But say, so that means you have a map in opposite direction, and this will be what we call Hopf algebra. So that's just the dual picture to the multiplication map. And from now on, let me Hopf algebra just H, and I will have this written with maybe curly letters or something to distinguish from base spaces. So basically, have a map of algebras. This is algebra map. Algebra map. We have a map of algebras from O of G to O of V, and call it gamma. Call it gamma. So basically, have a map gamma from a Hopf algebra to E, to something what should be the algebra of the total space, and then this Y, this is basically E mod G. So functions on the classes are invariant functions with respect to G invariant functions. In dual language, they are co-invariant functions. For this Hopf algebra, I will not go into technicalities. So you can, from the action, you can get the quotient. So similarly here, you could get a quotient, and then E co H into E will be inclusion of algebras. Inclusion of algebras. Will be inclusion of algebras, and because it's algebra map, it is a triple. Remember, at the level it is triple for the modules. So if you look at the categories of modules, then you have a three. You have like inverse image, direct image, and direct image has its own right adjoint. So now I want to have this kind of much more general. I would like to have group-like objects, not necessarily Hopf algebra. You know, Hopf algebra is just a very special case. If you have a Hopf algebra, then the category of modules over Hopf algebra is a monoidal category. So, and this monoidal category will have induced action on the category of modules over this thing which it acts. So what you will have in general, you will have modules over this, over H will act over modules over E or E. And this action has to be, you see, I want that this is kind of a group-like object in some sense. That means that I should know, well, that's a long story. I don't want to go into it. I should know what it means on the base level. It lives over some base scheme, say. So the base is here that when you work over a field, and you have you simply forget that these are modules. You take just vector spaces, and you do sorry. I forget for this level. I forget for the for modules here, I forget. So I know what it does on the vector spaces. It's just the usual thing. And I have that basically this action is geometric in the sense that it lifts its definition action. So this is action which basically, from reconstruction of which you can basically say that this is kind of group-like object. And the fact that it lifts upstairs means certain kind of structure of compatibility, which we call distributive law or entwining structure. Entwining structure. So that means that the action or coaction of the group, there are many examples, or Hopf algebra, will have to be somehow compatible with basically lifting structure from just having no geometry, just the base geometry, to geometry over E. And this will give many examples how you can lift that. And the most simple one is this, which we had before, that we had this principal bundle in affine case. In affine case, it was simply, as you say, this was some algebra, and this action became coaction. Everything was dualized. But in general, I can do this situation with nothing affine, nothing affine, and say that this monoidal category is basically that its action is induced by action of monoid object in that comonoid object in that category, also some sort of generator. Then comonoid in monoidal category will give a comonad. And this is the most often situation, that you have a comonad that's a comonoid with respect to this vector product. So it's like usual monoids, you know, you have monoid M cross M into M map. Now in comonoid would be some tensor product, M into M tensor M, with some associativity or so on. So you do the same in the category of endofunctors, monoidal category of endofunctors. This would be comonad. And another example of comonad is the comonad which will tell you about gluing those parts. If I take this product category, so one G comes from it's unfortunate that G is the same as group was G, but now I put comonad G, but it's also fortunate because this G is telling me about comes from group. It's not a group anymore, but it's a comonad on the category of space on which I act. Space is represented by a category with distinguished structure sheaf, and it comes from a group, and it can be represented by a command. There are recipes in big class of cases, recipes, and there are some general philosophy how to get these recipes. Comes from group action. And another one is that I have, say, a product of those categories B alpha, and on this product, the gluing data which are given by those functors. You remember, I have A into B alpha. Now, if I want to reconstruct A by forgetting A, I just have B alpha. I have B alpha prime, and so on. So imagine that I go from B alpha by direct image functor to A, and then by inverse image functor to B alpha. Then I have a map from B alpha to B alpha prime, and so on, from B alpha prime to B alpha double prime, and so on. So in general, I have from product of B alpha to product of B alpha. That's endofunctor. It's a functor from category to itself. So you have this big category, and there is all these maps together will form endofunctor on this product. And this endofunctor will also have a co-multiplication. And this will be a comonad for gluing comonad. And then if you have this category B alpha, then simply from this gluing comonad, there is a formal construction how to get basically back A under assumptions on this cover. So there are assumptions on this, and I can get back this cover, back this original category A, the same as I could get from this gluing data. Now, this entwining structure here will give me the following. Journal new page after. So I will have the following. I will have these categories. I will have this A tilde, down there are A. I have here action of G, and I have here B B tilde alpha. Here I have B alpha. So here I will have some G alphas. So this is like this G, it's like the same external group acting, but it's acting on the pieces. That is, of course, some assumption. You should, if I have here this F upper star that I am basically restricting. So this is usually a localization functor. I want to avoid the technicalities on these functors. And I want that this F star be compatible with G. So all these F stars form together this omega. So I want G omega and omega G to be isomorphic in some sense. And that is, again, a distributive law. So you want to have a group action on the whole thing, which will get this G alpha. But other way around, you can have this B alpha tilde just given with G alpha. And you want to compare this G alpha using this omega or pieces of omega, and to reconstruct back this A tilde. And so I want to, so if these G alphas agree on where should they agree? So if I have this B alpha tilde, I go first back to A tilde, then I go to B alpha prime. So I go from one to another. Now, if you look essential image of this composition, it has essential image will be some essential image will be some beta alpha, and then one more time kind of restricted localized alpha prime. And in general, this is different from B alpha prime alpha. So in non-commutative geometry, you have a usual phenomenon that if I have two open sets, U alpha cross U beta, and you consider, say, something like this will be the same as U beta cross U alpha. But in non-commutative case, analog of this is not holding. You have kind of, if I have two small categories, and I have direct and inverse image functors which help me to go from one to another, and you look at essential images, this will be like intersection, this essential image. So I'm restricting this to this other category. So it means somewhere in between. But I will have two different results. And if I compare an object here, if I want to compare them, I have to compare them both in this and both at the other in the other intersection. That's a phenomenon. Now I would like I still have a picture in which I didn't put the condition that something be you see, I had an example before motivating, but I didn't say when will this be really kind of principal bundle for this action. I just have an action, and I have now some categories here which I get from well, in an example I get from coinvariance. You know, you took the quotient locally, globally quotient. So here's, I want situation that this here is affine, so that B alpha are modules over a single algebra, and this is not affine. But I would like in general to know it's affine or not, whether each of these arrow is a principal bundle or not. And the thing is the following: if I have this A tilde, I have G on it, and I can make this some sort of invariance. So this is called Eilenberg-Muller category, but it is some sort of invariance. So there is a pair of adjoint functors between this and the original, because you can forget. So there is a pair of adjoint functors between these, and I want that this pair of adjoint functors is actually affine map. That means it's a triple. So you want that so you have this map. You want that that in this direction it's affine map. That means if this here would be in the classical case when I have E co-invariants of H and I have E, then this is really obtained from this here is really the generator in this category. So if I get the generator in this category, which is a single algebra, and this algebra is embedded in this algebra, then that's it. This is principal bundle, this is Galois. So that means I have just to reconstruct affine thing, but in general it doesn't need to be affine thing. I have this just a category, and this map has to be affine. That means I have a triple. In this case, if I have a category which embeds in the category of modules over this by affine map, then this has to be affine as well. So there is no need to require that anything is affine. For me, if I have a geometric action in the sense that it lifts lifts some sort of natural action over the base scheme, and if you look at the coinvariants, that the coinvariants embed affinely inside, for me this is a principal bundle. That's a natural condition. In affine case, this exactly, and if the monoidal, if this comonad is induced by the coaction of a Hopf algebra, this is exactly the situation. That's a theorem. That's easy theorem with what we know nowadays. For those who are in commutative geometry, what is analog of this? If I have E is a principal bundle, and you have a quotient E cross G, then if you look at the category of sheaves over E, and you look at which are equivariant, which are G equivariant sheaves, this is equivalent to the category of sheaves over the base. That's called faithfully flat descent. That's faithfully flat descent along torsor. So principal bundle in commutative algebraic geometry is called torsor, and the sheaves, the equivariant bundles or equivariant sheaves over the total space are the usual sheaves over the space of orbits. That's a standard thing. So you put this as a definition, plus you require that in algebraic situation that the original inclusion is affine, and then you call this a principal bundle. Now let me remind you that in classical case I had also, if everything was affine, I had this gamma. Gamma was mapped from a Hopf algebra, from Hopf algebra to the total algebra of the bundle, Now I want this situation. So what I want to repeat the same situation I had upstairs, but all this beta alpha tilde, each of those was some E alpha modules, and if each of these E alpha had a map gamma alpha from H to E alpha. I have such a map, and and I have a gluing data. But because gluing data are now defined completely in terms of algebras, I don't need to work with comonad anymore. So this omega, the comonad, will be more like what I had at the very beginning upstairs, you remember I had that Svidler coring when I had usual algebra, then I had this, I didn't call it Svidler coring, I should call it now. Where is it? Better right now. So if you have this map R to S, so I will take all these E alphas, and the category, if I have modules over E alpha and I have modules over E beta, then the functors from E alpha to E beta will correspond to bimodules. You know, good functors, that's called Eilenberg-Watt's theorem, good functors among abelian categories are basically tensoring with the bimodule. So what I will do is I will take the product of all these E alphas. That would be one ring. And I will have product of all these bimodules, E alpha beta, which will be another ring, S. Sorry. Oh, I'm doing it wrong. Sorry. This is a ring, and this will be a bimodule. So if the ring is S, analog, this E alpha beta is basically something like E alpha cross E beta over something, not necessarily, but it's something of that kind. So basically I have some bimodule. So in the case that I have extension of rings, then such a bimodule is S tensor S over R. It has a co-multiplication into S tensor S tensor S tensor S twice over S, co-multiplication over S, which basically takes S1 tensor S2 to S1 tensor 1 tensor 1 tensor S2. That's called Svidler coring. Now this is one situation. I want to have some. This is when I have just extension of rings. Here I have a more complicated situation. I have some bimodule which glues, and I have some ring. So I have in general some situation that I have co-multiplication in the situation with rings and bimodules. So co-algebra in general co-algebra in the category I have rings, bimodules, and so I have a usual bicategory rings, bimodules, and bimodule morphisms. This is like a monoidal category, but you have also different objects. It's called the bicategory. And so if you inside put the analog of comonoid, it's called the coring. And coring is basically given that you have algebra plus bimodule and plus coaction, and there is co-unit. I mean, there is a little bit more, but you basically have algebra and bimodule. Bimodule is where you glue. This is like those functors before when I had a direct image functor and then inverse image functor from alpha to alpha prime. Now, what do? For the situation, we have such situation both upstairs and downstairs. So I have this E alpha beta, but I have downstairs this co-invariance, which I will call U alpha beta, and of course U beta alpha and so on. And these are like co-invariants here, and this will be co-invariance here. That means that I have to have actions here and here. Like before I had this G is replacing is replaced by, because I am at the level of algebras now in these pieces, by Hopf algebra H. Globally, when I glue them, I don't have Hopf algebra anymore, but I have its category of modules, which is monoidal. So I have the situation with geometric action globally. So this is the local situation. I have to glue it just to a category. I do not glue it to modules over a ring. It is more general category. But on the level of each of these, I have the situation like before. I had U alpha, I have E alpha beta, and I have this gamma. I have this gamma from H. Gamma here and gamma here. I will have gamma from H to E alpha, and maybe I will have something like this here. Now, there is a classical result of Doi from 1980s, 1985 or so. He's a Hopf algebraist, and he considers such situation when you have, we say, comodule algebra. This is E is H comodule algebra, That's situation with each E alpha now in the situation upstairs. So if you have gamma alpha from H to E alpha, then you consider this E alpha coinvariants, and you tensor them with H. There is a isomorphism of vector spaces with E alpha. Basically, every element here can be written as sum of some coinvariants UI. They are in alpha, but forget alpha. We are just for fixed alpha doing U alpha gamma of some HI. This is how they look like. This is like saying that the principal bundle is trivial. That means you have basically direct product. But here is not direct product. It is a tensor product as an algebra. It is also tensor product as with respect to coaction of H, but in a little different sense. And but it's not quite. You see, this is the product of these such ones. When you put U with another U prime I J, say gamma HJ, for example, then these do not commute. I'm in non-commutative situation, so we will have something like UI, UJ prime, but not quite. I will do gamma HI, UJ prime, gamma HI1, 2, S, gamma HI3. Now something horrible. This is something from Hopf algebra theory. You can this here is basically nothing. It's basically something this is something like, this is epsilon of HI2 or whatever. This is something what is expanded from the unity. This is something proportional to, this is scalar, something proportional to 1. So I can insert this. And then this part here will be HI1 acting on UJ prime. So we'll have certain action, and this action depends on gamma. So this gamma is gamma alpha, so it depends on alpha. So what is the situation? The situation is that basically you can take this, but these are invariants. So that means that if you take the coinvariants of H in E alpha, then you have, because of this gamma alpha, you will have action on this algebra. There will be some delta alpha. So don't call it E alpha anymore, call it U alpha. Why I want to call it U alpha? I don't want to, on E alpha, I have some action. I will reconstruct that action from this delta alpha. That's what Doi says. Now I say more. I want to construct a different bicategory in which I will take such actions into the definition. So I will have two categories, two bicategories. One bicategory upstairs, and another is bicategory downstairs. So upstairs, I will have, you remember I had rings, better to say rings, bimodules, and bimodule morphisms. I will take, instead of rings, I will say algebras because I'm always working over a field. I will take algebras, but algebras which will have coaction of H. And not only coaction, okay, I will have, so these will be comodular algebras. That's one of the choices for the distributive law. You can do the same story for any other distributive law. So say comodular algebras. Then for this example is exclusively that, but there are some other bicategories which are interesting. Then I will have bimodules, also HX. And I will have maps, morphisms, which will respect that. Moreover, I will like that these bimodules be cyclic. That means there is an element which that everybody is obtained from this element. So that I can multiply, so I have some element, say it's C, and every element in this bimodule can be obtained that I multiply from the left and from the right by elements in algebra. So here is say that bimodule is over two algebras, say A and A prime, and there is bimodule M. Then I have here element C, and I take A on the left side, A prime on the right side, and this is the way I can get all elements of the bimodule there. So these are cyclic bimodules. And I would expect that morphisms of bimodules will have to respect the cyclic element. And downstairs, I will take again algebras, but no action of H. That's why I replaced E by U. I have different notation to forget. For E, there was always action of Hopf algebra or group or comonad or something, and I have no action here of that. Action on the space. However, I will have this delta alpha. That's some action. So I will have these algebras which have this delta, and this delta is respecting the situation that H is a Hopf algebra. Namely, if I act on the product UV, that will be H acting H1 acting on U and H2 acting on V. And also when I act on one, it's epsilon of H and I act on one. So I have algebra such, and then I have bimodules, which will have also like that. I call them bimodule measurings. Bimodule measuring means that if I act on U and then I have something in bimodule and V, then I will have a triple sum H1 acts on U, H2 acts on V, where of course, for those who are not familiar with Hopf algebras, this notation this is just the iterated coproduct on H. Will be some sum with some indices, and these indices are usually skipped, and that's called Swirler's notation. So here's M, and H3 acts on V. So this I will call bimodule measurings, and of course there will be again central. Cyclic, again cyclic, and morphisms of such. And now I want to have, if I have a comonoid here, so I'm claiming the Stojić theorem says basically that this here is the same as this here. It says that basically if you know this action, you can reconstruct back this. You take the tensor product and you have this isomorphism, so you can get E alpha basically as tensor product. And this, you don't have this gamma. You have gamma is trivial. It's just embedding this as one tensor H. H is embedding as one tensor H. But I have this action. Action tells me how to multiply these guys. It basically tells me how to commute, how to do this trick. And because I know this trick, I can get back to this. And this is this bijection of this is the Stojić theorem. But you can extend this to the whole category, to this whole bicategories, and you have equivalence of this bicategories. This here has actions, and these are data on the base space. So what are these? These are cocycles. So cocycles, you have a base space with some additional data, and you can reconstruct the principal bundle. That's basically the cocycle. So the cocycle will be the gluing data. That means in this case it will be just the comonad. So I don't call it. It is kind of a coring with additional structure. So the fact that it is cyclic, that basically means cyclic for coring. That basically means that if you have the Swidler coring, if I have coring has this product E alpha, and it has product or E alpha. Let be U alpha. Let be U alpha case. The same is upstairs, but I will soon write very explicitly, and then I can be finished. U alpha beta. So if you look at this guy, so call this U and call this C, and then you have a map C to C tensor C over U. This will be the co-multiplication and so on. And what cyclic basically means that you can take U tensor U, and this will be a Swidler coring, and you have a map of bimodules with respect to the coaction and so on, which is basically the coring map from U tensor U to C. And we will require that it's epimorphism. It's epimorphism. So this kind of structure, this is cyclic. That is epimorphism, because you have here one tensor one, because this is really an algebra. So you have one tensor one. In C, this is just a bimodule. You don't have one, but it has its image. Its image will be if the bimodule maps respect the cyclic vector in the bimodule, then you basically have to go to that object and then if you multiply with U here, with V here, you will get all elements. So all elements will be U times something times V. So this kind of situation has been in paper of Rosenberg and Kocevic in 1998, non-commutative, what's called non-commutative smooth spaces. But in coring theory, they basically say that we have a group-like element in the coring, and which is cyclic. This is a familiar situation, but we have now additional thing that we have these actions on every of these bimodules. So if the bimodule is with two indices alpha beta, then here is action on alpha, here is action on beta, and here is action alpha beta. You see, these are three different actions because you have bimodule you have two algebras and one bimodule. So bimodule has its own action, and the guys which act from the left and right have their own actions. And you have distribution on this, and you call this measuring. So it's not necessarily action. Measuring is a little less, but in these situations, it's usually action. I can do the whole thing when this is not an action, but it fails to be an action. But gamma is, we say, convolution invertible. That's so-called cleft extension. It's more general. You have category like this, where you have additional, instead of that, you have also delta alpha, this triangle alpha, but you also have some additional cocycle, two cocycle, which basically tells you how much you are away from being action. But still, this picture works, and we call it that then not actions but measurings. And then I have the same story. You have bicategory equivalence, and you can take comonads here, comonads here correspond, and comonads upstairs are basically glued principal bundles, total spaces, and downstairs are the cocycle data. So I will just, for the end, I will just write how concretely this looks like. So you have Hopf algebra H is a Hopf algebra. And then I have action alpha on U alpha. This will be action, which is a Hopf action. That means that it's also measuring. Then I have these actions on U alpha beta into U alpha beta. But I don't need really alpha. I could simply say single U. And here you could take a single coring. It can be any coring. And then you have the cocycle condition that if you take if define y alpha beta of H, you define that this is H acting on acting on the image. You have this distinguished cyclic object. You take the cyclic object in alpha beta. So this will be some map in alpha beta. Then you have the following thing, that in C tensor C over U, that means in triple intersections, you have that alpha beta of H localized to triple intersection. So not exactly this, but image of that in triple intersection. This is in double intersection of some y alpha gamma of H1 times y gamma beta of H2. And this is the cocycle condition. Now, what is amazing is that this cocycle condition intertwines two different coactions. One is H goes to H1 tensor H2, that's coaction of the Hopf algebra. And another is coaction of the gluing data, which goes alpha beta goes to alpha gamma gamma beta. That's basically the way you do the gluing comonad. Of course, I didn't need to put alpha beta. I could have put here basically write this in terms of general coring, and then it makes sense for general coring. Now, one more thing at the end, which is in the abstract, how to compare different colors. Now, this is a long story, but I will make it short in 3-4 minutes. Compare different colors. It's a tricky thing, in fact, compare different colors. And I better understand it not for general corings and general gluing comonads, but basically when comonads come from localizations. So if you have these guys, so you have one cover of A, and you have another cover of A. This is given by one comonad omega. This is given by one omega prime, or a coring, or it can be coring C, or it can be C prime. Now they can have they have different bases. Here is U, here is some U prime. It's not the same thing. So now you want to make a cover which refines the two covers. So something is missing. You see, if I put all 6, say here 3, and I have another 3, that means I have this 3, and I know how to pass in between. This is in all the data of this. I mean, this is not just endofunctor; it's a comonoid in endofunctor. So it has also this that I do push forward and then pull back. This push pull maps. I have between these, but I don't have between this and this. Not only that I don't have maps, I don't have even bimodules. So you need to have additional bimodules and additional to compare them. So, but say that you have now this omega, and I want omega to compare with something where is both omega and omega prime and some additional bimodules and other data. So I want to have such that when I look at the category of modules here and category of modules here is the same category. I have to have the same category. So basically, you do it in two steps. First, you make it kind of free extension.
Zoran,
That yes.
Very quick, right?
Yes. So you first make a free extension that basically, in the most free way you do it, that there is no data here, and then then you get basically the same arrows, and then you compose it with the map which has the same arrows, but the other data are not clear. So the first map has to be equivalence of categories, and second map can be whatever map of comodules, or sorry, of comonads over the same base, the same base. So then if you can do that, then of course to this wise you add additional ones likewise, but for alpha and gamma are now in different colors, and they still have to satisfy the same relations, and these are the data for the refinement. There is one more thing which you have to care, that not only that it's equivalence of categories, but in a way that you keep the track of category, because what you can have kind of the category look the same on the east and the west, and you make automorphism that west replaced by east and east by west, and you kind of wrongly attach it. You will have equivalence of categories, but you will simply glue the wrong parts of the space. So you have to keep track of basically that you have canonically along the same thread of taking the colimit of when you want to identify the cocycles, so that I have the classification of cocycles. So classification of cocycles first do for a fixed cover, and then you compare different covers by embedding into bigger covers. And in that you have to do a lot of care. There's also set theoretical problem that by modules you have, it's a full class. So the question is, if you have this S goes from, remember, I had from U times U to C, and this S, if I take basically the kernel of S, this kernel is isomorphic to the module, and the kernels are, so these kernels are not that many. So you can basically get rid of set theoretical questions as long as you work with monoids. If you work with comonads in general categories, then it's more complicated. Of course, here the full category is general, but the pieces are affine. You can have also that the pieces are not affine, then corings won't work, but comonoids will work. So basically you have a very explicit, you see cocycle, you have coactions on the base algebras, you have the gluing data, which are basically coming from these adjoint functors. They are basic maps of bimodules, and they give you part of the general story. So general story can be done at various levels of generality. So this is just an example which is most well understood because Doy's work is best understood, but there are many other cases where you can understand actions and gluing of principal bundles in noncommutative geometry in this framework. Thank you.
So Zoran, you stop?
Yes.
Yeah, thank you very much. Yeah.
Thank you.
Is there some questions, Rita?
Yes, I have a question, Zoran. So first of all, thank you for the great talk. I really enjoyed it. I have a question when we are talking about the G co-invariance or H co-invariance or G co-invariance. You remember that point? And so I didn't understand because you mentioned that you are more general. G is not a group. H is not an Hopf algebra. So how do you interpret the co-invariance? I missed that point.
Okay, so as I say, if you have a Hopf algebra, if Hopf algebra say coex on in the sense that you have a comodular algebra.
Yes.
Then you have induced action of monoidal category of modules over Hopf algebra.
Yes.
On the modules over the algebra on which you act originally. Now, the Hopf algebra itself is an object in the category of modules over Hopf algebra. So it's a monoid in that, it's a comonoid in that category. So a comonoid in when monoidal category acts on some other category, if you have a comonoid inside that comonoid will induce a comonad. If you have a comonad, the Eilenberg-Moore category of comodules over that comonad is replacement of the modules over the base space. And precisely in the situation when you have a space which is locally glued from modules over comodular algebras, then and if you glue the bases are the coinvariants on each piece. If you glue these modules over all these coinvariants of various pieces, globally you get exactly the Eilenberg-Moore category of the category upstairs.
I see. So this is what you call the coinvariance that glue the category, so to speak.
Yeah. So
okay.
the replacements for coinvariants.
Okay.
If the Galois condition works, so if
no, it's clear. It's clear.
Condition, in that case, it is the replacement of modules of the generalization of the modules over the covariance.
No, thank you. Thank you very much. Thank you.
I mean, it's quite amazing that this affine condition is all about Galois. It has been suggested in my last conversation. Rosenberg died in 2012 or 13. What was? And in the December before that, we met exactly to discuss what is the most general notion of principal bundle in non-commutative geometry. And after I explained him my examples and this geometric action condition for lifting, he understood it immediately. And then he said, well, it seems that this is enough. And then later I looked at the examples and it's really true. But I mean, he immediately kind of, after 1 hour of discussion, he got to suppose that general notion of principality of Galois is just affine condition of this Eilenberg-Moore category. Of course, if you don't have a monoid in this monoidal category, then what is the replacement for general action of a monoidal category, which is geometric? I don't know. There are some other examples where one can figure out, but in full generality, not. But if it's monoid or comonoid or some light generalizations, then it's exactly this. Of course, this also depends on I should mention, on work with Gabriela Bem. We had one unpublished work that if you upstairs, you have you have a comonad which acts compatibly with this cover. Then downstairs you have a cover with the same exactness conditions. So if upstairs I have gluing, downstairs I have gluing. Upstairs I have localizations, downstairs I have localizations, and so on. So if I have a good space with action which is compatible with the cover, then I induce very well-behaved base space. So in particular, these various pictures with coinvariants and so on work well.
Sorry, may I ask a small question? I remember you have some examples which involve, some quantum Grassmannians and so on.
Yes.
But any other examples? Can you? I don't know, because quantum Grassmannians is a pretty long story. But is there any simple example which would illustrate all these principles, or at least some of them?
Well, there were examples earlier than my work, in a sense, not for this general story, but for the non-affine principal bundles, or to bundles which have pieces. I mean, Majid and Brzezinski consider a cover of 2 pieces for this what they call quantum instanton bundle, and they had 2 pieces which were really localizations, and on each of them they had a cleft extension as far as I remember, and they together glue to one big Hopf-Galois extension. So Hopf-Galois extension is the affine case of principal bundle for this. This example is considered simple. I myself don't consider it simple because they, but over there you can put also connection. Of course, one can ask here whether you have the notion of gauge transformations. You do have, and you can say on the affine pieces there is a well-known notion of a connection for the differential calculus. So can you glue them along these morphisms? And you can glue that. I never really wrote down the whole story, but the simplest things are easy to check, and it's not difficult.
I see. Thanks.
Of course, when you say flag varieties, you see, and Grassmannians, one question is usually one has that the total space is affine, and that the base space is something like projective and consists of pieces. So globally, on the total space, you really don't need the many pieces, but you need to disintegrate into many pieces to get the basis, because globally you don't have the base. You have as a signal algebra, but you have the pieces. But of course, you can do the following. You can take 2 parabolic subgroups. 2 parabolic quantum subgroups, and take the say quantum SLN modulo 1 parabolic and modulo bigger parabolic. Both are kind of generalized flag varieties, quantum flag varieties, and then you look at the map in between. The map in between is not a principal bundle. It will be a bundle whose fiber is a homogeneous space, and this homogeneous space is itself obtained from gluing. So we have a gluing of pieces, in each of pieces is glued, and it's associated to original principal bundle for the smaller flag variety. So there are examples which are even not affine at any level, neither fiber nor base nor this, and belong to this story.
Thank you. I see. Thank you.
Is there more question or not? But it is only close to 3.
So
thank you very much,
Okay.
Zoran. Yes, Svato,
I have
please.
a small question. Do you know examples where when the invariants you spoke about them are Morita equivalent to the original ring or comonad? Do you know anything about the Morita equivalence of the dual picture? It's maybe well known, yeah. So
I didn't quite understand. Co-invariants are Morita equivalent to what?
At least so. I was interested in Morita equivalence for a couple of for some time. You started with Morita equivalence, and then I felt that then I would ask whether you have also some information about Morita equivalence regarding these dual objects you introduce, or these comonad objects. Or some things regarding imprimitivity theorems for the invariants. This is some question related to physics.
I don't know, but I wouldn't say that it behaves that well with respect to Morita equivalence there. I mean, you see, one of the phenomena was, which kind of turned me away from that, was that if you take the quantum function algebras, then the analog of the Gauss decomposition, the shifts of the main cell are not in general even Morita equivalent to the main cell, and that's kind of strange. Shows that
What kind of shift?
I don't know.
Okay. Isn't it a shift like in Verma modules by this action by which you subtract something? Maybe, no, I don't know. I don't.
Yeah, hard to say. I mean, yeah, there is one additional problem. If you take the universal non-commutative flag variety and compare it to the quantum flag varieties, then there are more characters than you would expect on that level. So if one would, I don't know, because it depends on flatness. Flatness kills some of these problems, and some of the induced maps are not flat. The covers are flat.
Depends on the ring very much. It depends on the ring very deeply.
Yeah, it depends on the ring, of course.
Okay, if there are no more questions, let us thank the speaker again. Yeah. Thank you, Zoran. That's a really great talk, and yeah, I hope that you should got the new invariant more with your construction. Yeah.
Thank you.
So